All right, so now that we've got our character stats, we can start on genetic variation. So first we need to know how many dominant alleles we have. That's how many big letters we have. So in the thumb category, we don't have any dominant alleles. Those are all small. So for the thumb, dominant, 0. Recessive, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10, so our total is 10, okay? The hair, we've got 1, 2, 3 dominant. So we've got 3 dominant with the hair. Then we've got 1, 2, 3, 4, 5, 6, 7. Recessive, we've got 7, which gives our total 10. Okay, so tongue, 1, 2, 3, 4, 5. We've got 1, 2, 3, 4, 5. 5 dominant and 5 recessive. So now that we have those, we can figure out our total of dominant. So we've got 5, 6, 7, 8. We've got 8 total dominant alleles in our family. There are only 8 alleles that we have as a family unit that will beat out other people's genes. Recessive, 15 plus 7, that'd be 22. And then total would be 30, which checks out. So we only have 8 genes in our family that would win out, and 1 was brought in by dad, and the other was brought in by mom. And as we have populated, we've split up. We said mom has this dominant for tongue, rolling, dad does not. And then we split, and Amber got it, Taylor got it, and I got it. So, unless we actually know, there's nothing we can do. Our children, unless we marry someone who is recessive, and our odds are that 25% chance. Whoever you marry, so Amber and, that shouldn't have been there, that should have been here. Amber and David, I don't know his, but it doesn't really matter because your children have a 75% chance of being able to roll their tongue. And then that chance will continue to grow until it's just 100% chance, and that recessive has just died. That recessive that dad brought in just died. And Taylor, same thing. Your kids, unless Maddie is recessive, and you have that 25%, you've got a 75% chance that your kids are going to have that trait for tongue rolling. So that's kind of how we can just check to see that makes sense. And then next, if we're trying to get our genetic frequency, it's the amount of dominant, so 8 so far. Gen frequency, we have 8 over 30 for dominant, and we've got 22 over 30 for recessive. And then, because I'm not very good at fractions, we invented a calculator. 8 divided by 30 is 0.267. 22 divided by 30 is 0.73. So this is called our genetic frequency, where we are, we have a 73% genetic frequency in our recessive category, and we have a 27% in our dominant category. So then we can take what is called the Hardy-Weinberg equilibrium equation, because we're in a species that has reached an equilibrium. Humans have reached an equilibrium. We don't evolve anymore, just like cows, horses, dogs. There's a large enough population with enough alleles that are inheritable and affect survivability, that we don't inherit them anymore. Our population's large enough that as a population, we have too much random selection going on to pass on any of these alleles in a way that actually matters. A dog that is white in a brown environment dies because he can be seen, but a human that can roll their tongue in an environment where humans can't roll their tongue isn't affected at all. So we're in what's called an equilibrium. And these two scientists, Hardy and Weiberg, worked out this equation to define evolution in an equilibrium, which to me just sounds like evolution is losing to design. So this is an equation that can test if a population is undergoing evolution, and it was originally put forth by two Christian scientists to prove that evolution didn't exist. And then a scientist that did believe in evolution took that equation and drew a little line right here on that equal sign and said, well, what you're saying is if these numbers don't equal up to be 1, evolution exists. And they said, yeah, but in anything that has a large population size, it equals up to be 1. So that shows equilibrium. That shows that evolution isn't a continuous process. It's a process that reaches a point. It allows speciation so that creatures can adapt, survive, and then once they can survive, once it's good enough that they can survive, it stops, reaches equilibrium. So then we can take P2, which is our dominant, 0.267 squared plus 2 times 0.267 times 0.73, our recessive, plus our recessive again, squared. And then we can say 0.267. So 0.267 is 0.071 plus 2 times 0.267 times 0.73. 0.389 plus 3 times 0.73. 0.533 plus 0.071 equals 0.993. So if that had equaled 1, it would mean that we don't have any genetic variation in us. It would mean that we are at an equilibrium. But because we're at 0.993, it means we have a 0.007 mutation rate. And that's converted to a percentage by moving this twice. So then you've got 0.7% chance of mutation. A 7% chance of mutation means that every cell in our body, all several million of them, billion of them, each one has a 0.7% chance that at some point in its life cycle between meiosis and it breaking down, it has a 0.7% chance it will mutate into a new cell, which could be a cancer cell, could be sickle cells, which we don't have sickle cells, but it could be any sort of cellular mutation. And there's a 0.7% chance that that would happen. And that means that in our family, starting with mom and dad, they created a 0.7% variation because they're not that different. Their only major difference is dad has hair on his knuckles, mom can roll her tongue. If we also had this thumb trait variation, and if I had factored more variations in, that number could change some, but the average genetic mutation variable for our family is 0.7%. And the way that we can tell that we are in a equilibrium is we can ask ourselves these questions. We can say, is there sexual or asexual reproduction? In humans, sexual. Is there a very large or small population? We're in a small population. Is there migration? Yes. We bring spouse in, we take spouse away, we move in and out from families, so there is migration in families. Is there mutation? Yeah, 0.7%. Is there genetic drift? Do we lose diversity in our family? Yes, we lose diversity because we're losing dad's diverse trait for not being able to roll his tongue. So, is there genetic drift? Yes, we lose diversity. Is natural selection happening? Do any of these traits affect survivability? No. Is sexual selection happening? Did any of these traits affect mom's choice of dad? So, did she pick him because he had a hitchhiker's thumb? I don't know. That would be odd. Did she pick him because he had hair on his digits? Still odd. Did she pick him because his tongue can't roll? I doubt it. So unless I'm wrong about any of those, sexual selection did not happen based on these traits. P and Q do not change, so our allele frequency did change, which means that we have 1 point in what would be called the evolving populations line, and then genotypic frequencies stabilize. Our genotypic frequencies did not stabilize, or they would have equaled 1, which means we have 2 points in the evolving line, and then the rest in the equilibrium line. So by far, we are in an equalized population. We're not evolving, we're not changing, we're losing diversity as we equalize. So the fact that mom and dad managed to kill a trait by getting together and pass on a dominant trait to 2 other children shows that as a species, we're getting rid of any trait that doesn't matter. If it doesn't matter, get rid of it, which according to the math here, we are equalizing. We're becoming more like everyone else. And that's what we're learning about in college. That's what your money goes towards. Darwinian evolution and how to apply it to a species and test it quantitatively. Because in science, if you can't prove it with numbers, it's not science and it needs to go somewhere else. So this is science. This is a scientific process that we can observe and we can recreate using bacteria, flies, rats, mice, all kinds of stuff. We can see how this genetic variation slows over time and they begin to reach an equilibrium favoring only the best traits. So if anybody ever asks how likely you are to mutate into Wolverine, or if your kids are mad because they weren't born with superpowers, tell them there was a 0.7% chance that they could have been born with a superpower.